Welcome to the Mole and Stoichiometry Part 3. Today we're going to talk about the mole and molar mass and percent composition. Let's go! So first thing is the mole, abbreviated MOL without the E. It's a fundamental unit for counting particles on the macroscopic level. So the definition of a mole is the number of carbon atoms in exactly 12 grams of carbon-12, also called Avogadro's number, named after Avogadro, although he didn't calculate it himself. The symbol is Na, and the number is 6.022 times 10 to the 23rd, although we'll usually simplify that to 6.02 times 10 to the 23rd. So what this means, and what the definition means, is that one single carbon atom, based on the periodic table, has a mass of 12 AMU. But if you have an entire mole of carbon atoms, that is 6.022 times 10 to the 23rd carbon atoms, that's going to have a mass of 12 grams. So the same mass off the periodic table can represent one single atom if the unit is AMU, or an entire mole of atoms if the unit is grams. So, for example, 1 mole of neon atoms has 6.02 times 10 to the 23rd neon atoms in it, and it has a mass of 20.18 grams based on the periodic table. If you had one single neon atom, that'd be just one atom, has a mass of 20.18 AMU. 1 mole of Cl- ions, chlorine ions, is 6.02 times 10 to the 23rd chlorine ions, which is 35.45 grams based on the periodic table. It even works for molecules. 1 mole of water molecules is 6.022 times 10 to the 23rd water molecules. I'm going to abbreviate molecule MLCS, which has a mass of 18 grams based on the periodic table. So we'll be calculating molar mass a lot. Molar mass is just the mass of a mole of atoms or molecules in grams. We're getting those numbers based off the periodic table. You may also hear it referred to as formula mass. Instead of what is the molar mass, you might hear as what is the formula mass. The formula mass refers to the basic unit in a network or ionic solid. And you may also hear it referred to as molecular mass. And so the molecular mass is for compounds that exist as molecules, or generally covalent compounds. So you might hear those words used interchangeably, just be aware of them. So find the molar mass of calcium nitrate, CaNO32. How many molecules of CaNO32 does this represent? So the mass I'm going to get off the periodic table, we'll start with Ca, has a mass of 40.1, N has a mass of 14, and oxygen has a mass of 16. Since this is O3, I'm going to actually multiply that 16 times 3 to get 48. Now, I see that overall there's 1 calcium, and there are 2 nitrates, 2 groups of NO3. So 2 groups of this 14 and 48. The way you can do that is 2 times 14 plus 2 times 48, or you can add 14 to 48, which is 62, and multiply that by 2. Either way, you're getting the same answer. We're going to take that answer and then add it to the 40.1, and you get 164.1 grams. That is the molar mass, so the mass of 1 mole of CaNO32. And so then that represents 6.02 times 10 to the 23rd molecules of CaNO32. Okay, so next, how many moles of atoms are contained in 56 grams of NO2? So the first thing I want is the molar mass off the periodic table. Nitrogen has a mass of 14, and oxygen has a mass of 16 times 2 because there are 2 of them. So 14 plus 32 is 46. So the mass of NO2 is 46. I'll start with the 56 grams that's given. And then it's a factor label problem from there. I know that 1 mole of NO2 has a mass of 46 grams. And since I'm asking for moles, all I'm doing is 56 divided by 46, which gives me 1.2174 moles. As far as significant figures are concerned, 56.0 has 3, so I'll use the first 3. That'll be 1.22 moles. The next we have is what is the mass of 2.5 times 10 to the 24 molecules of water. So the first thing we want is the molar mass of water, 2 times 1 for hydrogen, plus 16 for oxygen is a total of 18. So start with the number you're given, 2.5 times 10 to the 24. And again, I like to abbreviate molecule MLC because otherwise it takes forever. So I know that there are 6.02 times 10 to the 23rd molecules in 1 mole. Molecules in 1 mole of anything. That could be 1 mole of water, or 1 mole of NO2, or 1 mole of anything. But specifically for water, 1 mole has a mass of 18 grams. If you wanted to, you could skip that second step and put the 18 directly on top of the first step, and that would be totally fine. Because either way, you're going to multiply 2.5 times 10 to the 24 times 18 divided by 6.02 times 10 to the 23rd, and you're going to get 74.75. Looking at the significant figures, 2.5 has 2 significant figures, so we'll round this number to 75 grams. All right, one more mole problem. Bees release about 1.0 microgram, which is the same as 1.0 times 10 to the negative 6 grams of isopentyl acetate, C7H14O2, when they sting. By the way, that's also the smell of bananas. The resulting scent attracts other bees to join the attack. Calculate the number of molecules of isopentyl acetate released in a typical bee sting. So the first thing I'm going to need is the molar mass of isopentyl acetate. So I've got C7, that's 7 times carbon, plus H14, 14 times hydrogen, plus O2, 2 times oxygen. 7 times 12 plus 14 times 1 plus 2 times 16 gives me 130 grams per mole. That's the molar mass of isopentyl acetate. So I'm starting with what I'm given, 1.0 times 10 to the negative 6 grams. If the only thing they gave me was the micrograms, I would have to convert it, but since they gave me the grams, it'll make my life a little simpler. So now from that grams, I have calculated that the molar mass is 130 grams per mole. So that's how many moles of isopentyl acetate. But we're looking for molecules. So 1 mole contains 6.02 times 10 to the 23rd molecules. 1 mole of anything contains 6.02 times 10 to the 23rd molecules. Again, like in the problem before, you could skip the second step and put this 6.02 on the top of the first step. Either way, your 1 times 10 to the negative 6 times 6.02 times 10 to the 23rd divided by 1 mole, and you get 4.63 times 10 to the 15th. Using 2 significant figures based on the 1.0 that was given, my final answer is 4.6 times 10 to the 15th molecules of isopentyl acetate. So the next question, a tad trickier, calculate the number of carbon atoms specifically present in this amount. So this amount is 4.6 times 10 to the 15 molecules. That's the number of molecules of C7H14O2. So from that one molecule of C7H14O2, notice that there are 7 carbon atoms. There are 7 carbon atoms because it's C7H14O2. So we're going to take that answer that we got originally and multiply it times 7. Now, I'm actually taking my original number that was already in my calculator. I'm not using the 4.6 that I rounded from. I'm just taking that original number that I had times 7, and I get 3.24 times 10 to the 16th. Rounded to 2 significant figures, that's 3.2 times 10 to the 16th carbon atoms. On to percent composition. So typically percent composition will be the percent by mass. Sometimes you will hear percent by volume or percent by moles, but If it's just general percent composition, it will be by mass of each element in a particular compound. So any percent is a part over whole, so by mass, that's the total mass of the element, or the part that you're looking for, divided by the total mass of the compound, or the whole entire thing, times 100 to make it a percent. So find the percent composition of each element in CaNO3 This compound should look a little familiar. We found its molar mass just a little bit ago. So we're going to use that same molar mass. Ca had a mass of 40.1. There were 2 nitrogens, and so that total had a mass of 28, 2 times 14. And there ended up being 6 oxygens because there were 2 O3s. So that was 96. So if in the previous problem you ended up with 2 times nitrogen plus 3 times 2 times oxygen, you ended up with these numbers. And then overall, recall that had a total mass of 164.1. So if I want the percent calcium, calcium had a mass of 40.1 out of the total 164.1. So 40.1 out of the total is 0.2443 times 100 is 24.4%. Now on to the nitrogen. So for the nitrogen, that's going to be 28 over 164.1, not 14 over 164.1. And that is because out of that 164, 28 of it was nitrogen, not the mass of a single nitrogen. So when I divide that and multiply it times 100, I get 17.1%. And finally, we have oxygen. That's a total of 96 out of that 164.1 times 100. And we end up with 58.5%. It's a good idea to check yourself by adding together your 3 final answers, or however many final answers you have, and seeing if that's close to 100. And I believe in this case it is right at 100. If it came out to 99.9 or 100.1, that's totally fine. If you end up having all your percents add up to 74%, you've done something wrong, so you need to make sure and go back and check. All right, so another one. How many grams of carbon are contained in 55 grams of CO2? So I'm looking specifically for the carbon in CO2. So let's remember the molar mass first. Carbon weighs 12, 2 times oxygen, which is 16. So 32 plus 12 is 44 grams per mole is the molar mass of CO2. So that's telling me that carbon has a mass of 12 out of the total CO2, which is 44. Carbon has 12 out of the total 44. So this question is a direct proportion. How many carbons out of a total of 55? So if I had the total set up as 55 instead of 44, how many of those grams would be carbon? So we're going to cross multiply, which is multiply the numbers that are across from each other and divide by what's left. And we end up with x is equal to 15.0 grams. So there'd be 15 grams of carbon if the mass was 55, because there are 12 grams of carbon when the mass is 44. For this next one, I want you to try it on your own first. It's a little tricky, but I think you can do it. Pause the video now. So hopefully you did. This time we're going to calculate the molar mass of a metal, some random metal, that forms an oxide with the empirical formula M2O3. So the formula is going to be M2O3, 2 metals, 3 oxygens. It contains 68.4% of the metal by mass, and hopefully you look at that and think, that obviously means there's 31.6% of the oxygen by mass. So let's look at this problem again. Calculate the molar mass of a metal. So essentially what it's asking is, what is the mass of M? And I already know the mass of oxygen. So we're going to call M X and the total value Y. There's a couple different ways you can tackle this. You can think part over whole or part over part. For the moment, I'm just going to go with part over part. I know that the ratio of M to oxygen is 68.4 to 31.6. I'm getting those off of the percentages. I also know that the total oxygen in the compound, 3 times 16, is 48. What I don't know is the total M in the compound. I'm looking for this 2 times X. I know the 48 for sure. So that turns into a direct proportion. I can cross multiply. That's 68.4 times 48 divided by 31.6. And so I end up with 2 times X is 103.9. I'm actually looking for an individual X, the mass of one single oxygen, so divide both sides by 2, and I get that one single one of these atoms is 51.9 grams. So if you look off the periodic table, 51.9 grams per mole is the mass approximately of chromium. So that means my metal is chromium. Here's a different way you could tackle the exact same thing. You could say, what is the mass of oxygen compared to M2O3, the total instead of a part to part? Because I know that oxygen is 31.6%, that's 31.6 per 100, and I also know that oxygen is 48. Let's put that 48 on the bottom. Sorry, 48 on the top and the X on the bottom. So from there I'll cross multiply and divide. Now really that X on the bottom shouldn't actually be an X. Technically that's going to be the Y that you originally said, the mass of the total compound. So when you solve for that, you'll end up with Y is 151.9. Now the 151.9 is the total mass of the whole thing, so we're going to subtract the oxygen from it. So I end up with 103.9. That's the mass of 2 times X. So from there, I'm going to divide that by 2, just like I did previous, and get X is equal to 51.9, which is chromium. So that's just a different way to tackle the exact same problem. Okay, well I hope you've learned a little bit about percent composition. We'll see you next time.